Question 8. This question is about sodium and some of its compounds. Use your knowledge and structure of bonding to explain why sodium bromide has a melting point that's higher than that of sodium and also higher than that of sodium iodide. So you've got to talk about each of these in turn. We've got to consider what kind of bonding's in sodium. So it's metallic bonding. So you've got to describe metallic bonding. So it's got metallic bonding. What metallic bonding happens is the atoms release electrons which become delocalized. So the Na, the sodium, releases an electron, loses an electron, and each of the sodium atoms then become ions, Na pluses, and the electrons are delocalized. So there's an attraction between the Na plus ions and the delocalized electrons. That's a metallic bond. Next, sodium bromide and sodium iodide, they're ionic. So you've got ionic compounds. So what happens is the Na is in group 1, wants to lose one electron. Bromide is an ion, a Br minus ion formed from bromine. Bromine's in group 7, wants to gain one electron. So the sodium atom gives an electron to the Br. So this becomes Na plus and this becomes Br minus. There's going to be attraction between the Na plus and the Br minus ions. And the similar kind of thing happens in sodium iodide. That becomes Na plus I minus, and they form a giant ionic lattice, a large ionic lattice. So why then is sodium bromide got a higher melting point than sodium iodide? It's got to be something to do with the difference between bromide and iodide, and the difference is Br is smaller than iodide, and so you're going to get the ionic bonds are stronger, or words to that effect, than the metallic bonds. You can say that first of all. And there's a stronger attraction between the ions in NaBr than there is in NaI, and the reason is that the Br ion is smaller than the I minus ion. So if the ions are closer together, then you get stronger bonding. Question 8.2. When 250 milligrams, or if you divide by 1,000 to get it into grams, 0.250 grams. Remember, if you go from milligrams up to a higher unit value of grams, you divide by 1,000. Added to 500 centimetre cubed of water at 25 degrees C, a gas was produced. Write an equation. Well, sodium's a metal. With water, it'll make hydrogen gas. So sodium makes sodium hydroxide. A metal and water always makes the hydroxide, unless it's something like magnesium with steam that will make magnesium oxide. But in cold water it makes the hydroxide. I know hydroxide is OH1 minus, Na is Na1 plus because it's in 1 plus oxidation state, it's in group 1, so it's just NaOH, and you make some hydrogen, and you can balance that by putting half H2. Then what happens? So what we've got is we've got Na, we've said we've got 250 milligrams or 0.25 grams. We know the MR of sodium is 23. We can look that up in a periodic table. So moles equals mass divided by MR. Mass is 0.25 divided by 23. So I've got 0.109 moles of sodium. Now, 0.109 moles of sodium will make half the number of moles of hydrogen, because 1 mole of sodium makes half a mole of hydrogen in the equation. So if we divide this by 2, I'll work out the number of moles of hydrogen. So number of moles of hydrogen is this divided by 2. It's 5.43 times 10 to the minus 3. You're allowed up to 4.45 times 10 to the minus 3, so it allows some error on your calculator. Okay. Next thing then, we can use PV equals nRT. We've got a clue because we've got R. So PV equals nRT. What do you need? Pressure has got to be in pascals. 101,000 kilopascals. 101 kilopascals. So to get that down into pascals, then we multiply by 1,000. So a large unit value into a small unit value, you multiply by 1,000. So that becomes 101,000 pascals. We've got to get the temperature into Kelvin. So 25 degrees C, you add 273 to convert degrees C into Kelvin, 298 Kelvin. Now we can use PV equals nRT. Pressure times volume is number of moles, which we've worked out before for the hydrogen. Remember, this is called a gas equation, PV equals nRT. So you've got to have gas. N is the number of moles of gas, the hydrogen gas. Always remember that you're talking about gases when you're using this equation. 8.31 is R, and the temperature is 298. And if you multiply this out and then divide by 101,000, then you work out that V is 1.33 times 10 to the minus 4. Remember, a volume in PV equals nRT is in meters cubed, and it says calculate the volume in centimeters cubed. So meters cubed down into a lower unit value, decimeter cubed, we multiply by 1,000, and then to get decimeter cubed into the next unit down, centimeter cubed, you multiply by 1,000 again. So you're going to multiply this by 1,000 and then by 1,000 again, and it'll come out as 133. They allow 134 as well. Calculate the concentration in moles decimeter cubed of sodium ions in the solution produced. So we know the number of moles of sodium is 0.109. We know that concentration is moles, 0.0109 divided by volume. Volume is 500 centimeter cubed. Convert that into decimeter cubed by dividing by 1,000. A small unit value like centimeter cubed up into decimeter cubed, a large unit value you divide by 1,000 is 0.5. So concentration is 0.0109 divided by 5 times 10 to the minus 3, or 0.5, and it'll come out as 0.0217. They actually allow 0.022 because most of these values are to 3 significant figures. So they allow it to 3 significant figures, except the 25 degrees C is to 2 significant figures. So they allow you to put your answer to either 2 or 3 significant figures. They'll allow both. Sodium reacts with ammonia to form NaNH2 that contains NH2 minus ion. Draw the shape. Well, let's consider nitrogen's in group 5. If it's got a minus, it's got an extra electron, so it's got 6 electrons now. It had 5 because it's in group 5. An extra one means it's got 6. 2 hydrogens come along and form 2 bonding pairs. That means there's 4 electrons left over, or 2 lone pairs. So it's got 2 lone pairs and 2 bonding pairs. It's going to be bent. It's going to look like that. We've drawn them as lobes like this. These are lone pairs. And so if you imagine that you draw them like that, and you might think it's tetrahedral, 1, 2, 3, 4, but it's not tetrahedral. Oh, by the way, we put the minus. We're not quite sure where the minus is, so we draw a square bracket around it and put a minus to say somewhere there's a minus. So I've got 2 lone pairs because nitrogen had 6 electrons, 5 of its own, an extra 1. 2 bonding pairs take up 2 of the electrons, 4 left over, 2 pairs. These are my 2 lone pairs. You might think that's tetrahedral because there's 1, 2, 3, 4 pairs, 2 lone pairs and 2 bonding pairs. Except it's not, because what actually happens is, first of all, you don't actually you don't actually see these lone pairs, so actually you consider this part, which means that it's V-shaped or bent. You actually don't take the lone pairs into consideration when you're looking at the shape of the molecule. You ignore these. You need to consider them to work out what the actual shape is, but you actually only look at the bonding pairs when you're actually describing the shape. So it's V-shaped or bent. And if it were a tetrahedral, something like CH4 with 4 bonding pairs, it'd have a bond angle of 109.5. Every time you replace a bonding pair with a lone pair, you subtract 2.5. So 109.5 subtract 1 lone pair, subtract 2.5 becomes 107. That would be something like ammonia with NH3 with a lone pair. Or if you have a second lone pair, then you take off another 2.5. So it becomes 109.5 down to 107 down to 104.5. What's the justification for it coming down to 104.5? Well, you need to talk about the electron pair repulsion theory. You need to say that electrons repel. Electron pairs repel and go as far apart as possible. That's the first part. And then you talk about the fact that lone pair repulsion is bigger than lone pair bonding pair repulsion, which in turn is bigger than bonding pair repulsion. And that's all you need to say.